It has become very clear in recent years that we need new approaches to limits in optical systems and components. We need to move beyond simple diffraction and constant brightness or étendue limits towards something that rigorously allows us, for example, to count communications channels and degrees of freedom, and something that can work even with nanoscale objects. It's tempting to try to reuse the ideas of modes in optics to do so. But there are many problems with that, not least the fact that the sets of modes we end up working with are infinite and hence are somewhat difficult to count. There is a way around this, and actually it has been hiding in plain sight for some time. But of course, not surprisingly, it requires us to think a little differently about optics. In this talk, I'm going to try to explain this approach, showing you how it solves these problems and gives us what, in a powerful sense, is provably the right fundamental way to look at complex optical systems. This talk is based on arguments in this reference here. For additional mathematical background, you could also look at this, although hopefully you will not need to do that. And if you would like a copy of these slides, please just send me an email. We are used to modes for resonators, such as a mass on a spring resonator or a standing wave resonator, and for propagating modes in waveguides. We like modes because they are economical. We can use a few mode amplitudes, not fields at every point, and we can often count modes meaningfully. Modes have very useful mathematical properties, for example, orthogonality and completeness. And we can give a definition of a mode. A mode is an eigenfunction of an eigenproblem describing a physical system. But because it's an eigenfunction, that's why modes have these properties. But when we look generally at communicating with waves, or scatterers or optical devices or nanostructures between some source and receiving volume, we need a different kind of mode that looks at these source or input spaces and receiving or output spaces. They are modes in two spaces, not one space. They are not the beams between the spaces. To set up the mathematics of this problem, we consider two spaces. First of all, a source or input volume or space, which we could describe as Vs for the volume, but more rigorously we're really talking about a space of functions, technically a Hilbert space, that we could call Hs. And this space can contain the possible source functions, and we'll write these using a Dirac notation for convenience, as I've shown here for this function psi s, so representing some source. Similarly, we will have a receiving or output volume, Vr, or more rigorously, really this mathematical Hilbert space of functions, Hr, which will contain the possible wave functions. And again, we will write those functions using a Dirac notation for convenience, here phi r. The sources in the input space give waves in the receiving space through some coupling operator, which we'll call GSR here. For free space, this would be based on a free space Green's function, such as a scalar monochromatic Green's function like this one here. And what a Green's function does is it gives the wave at some point RR in the receiving space that results from the point source at RS in the source space. Now, we want eigenproblems to get modes, but we need two eigenproblems because we have two different spaces. And these are not, therefore, just the usual eigenproblems of, say, a resonator in each volume. There is, however, a key mathematical trick we can use instead. With the coupling operator GSR between the spaces, for the source space, we can solve the eigenproblem for this different operator, the product of G dagger SR and GSR. So we solve this eigenproblem for this operator, G dagger SR times GSR. The solutions to this eigenproblem give us an orthogonal set of source functions, so psi Sj, in this Hilbert space Hs. Incidentally, The Hermitian adjoint of GSR as a matrix would be the complex conjugate of the transpose of GSR. And as a Green's function, it's a complex conjugate with the source and receiver points interchanged. With the coupling operator GSR between the spaces, for the receiving space, we solve the different eigenproblem for the operator GSR G dagger SR. So we've swapped them around in order here. So we solve that to get an orthogonal set of wave functions phi rj that are in this other receiving Hilbert space HR. Note incidentally that these two problems have the same positive eigenvalues, the modulus squared of this number Sj. Now, when we have solved these two problems, we find that if we operate on one of these source eigenfunctions, psi Sj, with the coupling operator GSR, we get Sj times the corresponding one of the receiving eigenfunctions, phi rj. So the source eigenfunction generates the corresponding eigenfunction as the wave in the receiving space, with this coupling amplitude Sj. Therefore, we have established the communication mode pairs of functions. Note that, by our definition of modes that we gave earlier on, each one of these two sets of functions, the source functions psi Sj and the received wave functions phi rj, is a set of modes. The modes in one space are paired with those in the other. In practice, we only have to solve one of the two eigenproblems. We can deduce the solutions to the other one from, for example, GSR operating on psi Sj gives us Sj times phi rj. This mathematical process is actually the singular value decomposition of the operator GSR. For any linear operator we can think of, D, which we may think of as a matrix for convenience, at least as long as it is bounded, that is, it has a finite output for a finite input, we can perform the singular value decomposition. That is, we can write it in one of the following two equivalent forms. Here as a product of operators, which again we can think of as matrices, and here involving the functions. These are exactly the same, by the way. U and V here are unitary operators, that is, power-conserving operators if you like. D diagonal here is a diagonal operator with the elements Sm. And these are called the singular values. The psi m are the columns of U, and the phi m are the columns of V. Singular value decomposition has been around in mathematics for well over 100 years. This use in optics is much more recent, being introduced first in 1998. And various groups have picked up on this idea since then. It has also been reinvented by others. It is, however, not widely known, even though it turns out to resolve many problems and paradoxes. Here is a short list of the history, though I won't go through this in detail. This paper is a full introduction to this singular value decomposition method and its results, including full functional analysis mathematics, radio frequency, acoustic and optical examples, several new heuristic behaviors we get from this approach, full electromagnetic and quantum extensions, and fundamental physical results. A key point is that this new two-volume singular value decomposition approach immediately gives us a sum rule. And that is ultimately what imposes limits, including the most general version of diffraction limits. And this limit solves the problem of infinite sets of functions. Note that for the matrix elements of D, which we could call Gij, evaluated on any orthonormal basis sets we like, the sum of the modulus squared of these matrix elements is the same as the sum of the modulus squared of the singular values. And we can usefully write this as a sum rule S. This sum rule is important below for many reasons. It can be evaluated without solving the problem, and it gives a limit on the number and strength of connections. All of this may be simpler to understand if we construct some simple examples. So we imagine we have our source volume, our coupling operator, and our receiving volume, and we can see how this works first for a finite number of point sources and receivers. So for example, loudspeakers at positions RS1, RS2, RS3, and so on in the source volume, and microphones at positions RR1, RR2, and RR3, and so on in the receiving volume. Using the Green's function, we can construct the resulting matrix to represent GSR. So let's consider three sources and receivers. A set of source points, which we could think of as loudspeakers, a set of receiving points, which we could think of as microphones. There's some separation between them. Here we've chosen that as just 5 wavelengths, and the sources themselves and the receiving points are separated just by 2 wavelengths. For these source and receiving points, then we can simply use this Green's function to calculate all the matrix elements. It's straightforward. And that gives a matrix that looks like this, presuming unit wavelength for simplicity here. This contains all the coefficients coupling the source points to the corresponding receiving points. Note incidentally that the sum of the modulus squared of the matrix elements in this matrix is the relevant sum rule here. So we get a specific answer for that, a specific number. With this matrix, the orthogonal eigenvectors of G dagger G are these 3 vectors. And the corresponding eigenvectors of G dagger are these 3 vectors. And in this symmetric problem, these happen to be the complex conjugates of the source vectors, though that is not generally the case. So these solutions that we have here are essentially unique. There is only one set of such orthogonal channels. The modes then are these complex drive and receive vectors, not the beam in between the sources and receivers. It's these vectors that are the solutions of the eigenproblems. These are the modes. The modulus squared of the singular values are the power coupling strengths in this problem. So these numbers here that we get from that eigenproblem. So we see first of all that the channels are not all equally strongly coupled. These numbers are somewhat different. 3.41, 2.89, and 1.37 on the top line, with the same denominator throughout. Note incidentally that the sum of these power coupling strengths is the same number we got before by adding up the modulus squared of all of the matrix elements. So the coupling strengths of these channels use up the sum rule. How would we use a communications mode? Well, the idea is that a given source vector gives the relative amplitudes and phases to drive the 3 loudspeakers to drive a particular communications mode channel. So this vector of relative complex amplitudes here. And a given receiving vector gives the relative amplitudes and phases for adding up the signals from the microphones to receive a given communications mode channel. So we add up the microphone outputs with these complex amplitudes. This would give us the first channel in both cases here. Optics, of course, does not easily have directly controlled point sources and receivers, but recent work with meshes of Mach-Zehnder interferometers allows us to construct arbitrary vectors of superimposed amplitudes from separate sources. So we can construct these vectors we've been talking about also in optics. Now, discussing Mach-Zehnder mesh architectures would really be a separate talk. I've given some references over here that discuss this topic. The basic idea is that we take Mach-Zehnders, like this one shown here as a waveguide Mach-Zehnder, or as a block here, and we construct meshes of interferometers, like this source mesh here and this receiving mesh over there. What this source mesh can do is it can take an individual input channel and construct an arbitrary vector of output amplitudes, here just shown as light emerging directly from waveguides. And similarly, this second input here can construct another orthogonal vector of amplitudes that come out here, and so on for the third one. So this can generate our point sources, as it were, from an individual channel, and we can have three different orthogonal such vectors of outputs here. Similarly, this receiving mesh can take vectors of inputs and it can sort them out one by one to these output channels. We can continue to look at larger problems with more source and receiver points. In this paper, there is a variety of examples, including ones with larger numbers of points and with one-dimensional, two-dimensional, and three-dimensional source and receiver volumes. Now let's look at a larger problem. This will be what we will call a paraxial example. Here we have two vertical lines of sources, but very close together, but this is for a technical reason to eliminate backward waves for graphic clarity. This line of sources is over here, and we have a single line of receivers. The line of receivers is over here, but now we have 97 of each of these. The dimensions here mean we are approximately paraxial. The picture we are showing here shows the cross-section of the intensity in the plane. Here, for what is actually the most strongly coupled communications mode in this system. So let's look at a set of these modes one after the other. I'm going to show you all of the odd modes in this system. So here's the most strongly coupled one. And on the right, we're showing the magnitudes of the power coupling strength, so the modulus squared of the singular values, as a percentage of the sum rule. So this first one takes over just 8% of the sum rule. The next one, mode 3, also takes a rather similar fraction of the sum rule. The next one, similarly. Mode 7, mode 9. And by mode 11, we're just starting to see that the wave is missing the receivers. So here, the wave is just about to begin to miss the receivers, and we see a slight fall off in the strength of the coupling. There are more modes here. Here's mode 13, and we see this phenomenon of the wave missing the receivers getting stronger. And if we go to mode 15, we see the coupling is very weak, and we can look at that on a logarithmic scale as well. It does exist, but we see it's mostly, on this figure here, missing the receivers. It's not totally missing the receivers. There's still a very small amplitude in the middle here that we can't see on this scale. And if we go up to higher modes, we see the coupling strength falling off exponentially fast. This paraxial problem then does show a number of strongly coupled modes that are all approximately equally strongly coupled, with this coupling strength here of just over 8%, and up to what we could call a paraxial heuristic number, NHY here. It's about 12 in this case. This paraxial heuristic number corresponds to our usual ideas of a diffraction limit, by the way. And we can call this approximate equality of the coupling strengths paraxial degeneracy. But beyond such paraxial degeneracy, or degeneracy from symmetry or from occasional accidental degeneracies, we have no freedom in choosing the communications modes. They are otherwise unique. In particular, once we have chosen the source and receiving volumes or surfaces and fixed the optics, we cannot increase the number of strongly coupled orthogonal channels beyond this singular value decomposition result. Once we have chosen our optical system, we have no freedom to choose a large number of less well-coupled orthogonal channels instead of a small number of strongly coupled orthogonal channels. Once we have deduced our communications modes and their coupling strengths, we know exactly how many orthogonal communications modes we have with coupling strength above any particular value. We count the number of bars that lie above the horizontal line. So here are 12 orthogonal modes that have coupling strength above this particular value shown by our horizontal line. Nothing we can do in choosing source or receiver functions will increase that number. We cannot regroup to get larger numbers of less well-coupled modes. Such attempts lead to functions that are simply not orthogonal. Now, we've seen paraxial degeneracy in the example we just looked at, but many or even most optical systems we can think of do not show this paraxial degeneracy. Such degeneracy is the exception, not the rule. For example, we can look at concentric spherical shells, and there are various other examples that I've also given in this article in these pages. The exponential fall-off past some characteristic number in the strength of the coupling that we saw in our paraxial case here actually appears to be common in many different situations, and it may even be universal. The uniqueness of the communications modes taken together with this exponential fall-off explains why focusing past the diffraction limit is so hard in optics. We can only, in fact, get linear improvement in resolution at exponentially increasing cost, essentially of the source amplitudes. And again, to see this in more detail, look here in this article. Now, we've looked at point sources, and we might reasonably expect that increasing the number of source and receiver points would give us an increasingly good approximation to continuous sources, and in optics we're interested in continuous sources such as wavefronts. This is correct that we can make this transition from points to continuous sources, but to prove this, and to prove that we will still get some rule limits and limited numbers of useful channels, we need to go beyond the mathematics of finite matrices. And this mathematics is functional analysis, and I've written a tutorial here. Fortunately, though that mathematics can be difficult, there are simple results that give us what we need, especially because the wave coupling operators are all what are called Hilbert-Schmidt operators. For some scalar operator g omega here, a Hilbert-Schmidt operator is one for which the integral over the source and receiving volumes, this integral here, is finite. This will be true for any wave operator with finite volumes, because finite sources always give finite waves. And this, although I've shown it here for scalar waves, also extends easily to vector waves. The Hilbert-Schmidt operators are all what is called technically compact operators. And that allows us to work with infinite basis sets and with continuous functions and still get finite results like the sum rule and its consequences. All physical wave operators are such Hilbert-Schmidt operators. So we get sum rule results even as we go to continuous functions and to infinite sets. This is a point that has not been fully appreciated in previous discussions of numbers of communications channels. Now, we also want to extend to electromagnetism. Electromagnetism, though, has vector fields, and we have two kinds of fields, electric and magnetic. However, we can formally create a new electromagnetic gauge that simplifies all of this, and as a result we can get similarly simple results in the end, even in this more sophisticated case. Essentially also, the results from the scalar case mostly carry through, with similar diffraction and sum rule behaviours. We acquire a new energy inner product for the electromagnetic field that lets us, for example, quantize the electromagnetic field for arbitrary volumes without artificial boxes. As mentioned before, with similar mathematics, we can handle the more general case of a scatterer or optical device or object, it could even be an optical fibre, that is described by some operator d in its relation between the source space and the receiving space. In this case, we may not know to start with exactly what d is, but we can still deduce some useful general results. One immediate consequence is that because we can always perform the singular value decomposition of some operator d here, there is a set of orthogonal channels through any linear scatterer. Other results include new modal Kirchhoff radiation laws, a new Einstein A and B coefficient argument that works mode by mode with just one coefficient, avoiding artificial boxes. And the conclusion here is that more deeply, the mode converter basis sets are the right fundamental description for optical objects and devices. These are very basic concepts in optics. So in conclusion, we've seen we can set up a new way of looking at waves. It is optimally efficient. It defines the very best possible modal basis sets. It allows a proper counting of modes. It resolves paradoxes of infinite numbers of channels. It gives us the best channels through any linear system, and it allows fundamental results for devices and for physics. As I said, here's the main reference to this work. If you'd like a copy of the slides, just send me an email. And I'm pleased to acknowledge my funding from the Air Force Office of Scientific Research. Thank you very much.